open parallel company.
Yes.
He's from New Zealand, and he's also specializing in high performance, the edge, the parallel, and the exascale computing. He's also have a background in strategic leadership, high tech, and engineering, mathematics, and venture capital, and holds a master's of entrepreneurship from the School of Business of the University of Otago, New Zealand. His presentation will be on the topic agriculture empowered by supercomputing. Nicolas, the stage is yours. Please, before that, please, if you have any questions for Nicolas, post them please on the chat, and then Nicolas will be able to answer them at the end of his presentation. Thank you, Nicolas. The stage is yours.
Thank you very much, Kiwi. Thank you very much. Good morning, kia ora. Good morning, everyone. Good evening for me. Greetings from New Zealand. It's around 10 p.m. here of the same day as you. I am Nicolas, and the topic today, agriculture empowered by supercomputing. But before that, I want to say how pleased I am to talk to this audience. I've been in South Africa a number of times through the SKA radio telescope project. I spoke at the conference in 2015, 2016. It's a new experience to be presenting live. So, but before we start, I want to summarize which are the core takeaways. Essentially, I want you to focus on three core topics, which are technology, the scale of the problems, and at the same time, the complexity and risk. And I want to highlight, if you only focus on one of them, if you only think about the scale of the problem, ignoring the technology background, you will left behind because someone else in your industry, particularly your competitor, will be combining technology at scale, addressing complexity and risk. And this goes in particular for agriculture, but in general to every industry. Now, who are we? Who is Open Parallel? Well, it's a virtual company. So even before the pandemic, we were already a virtually distributed company worldwide. We specialize in strategic high-tech platforms, high-tech generalists at low level of computing, particularly software, but also hardware for design. Some of our clients over the past decade, the most recent sign is the company named CodePlay, which is based in Scotland. They do acceleration for AI and heterogeneous systems towards exascale. And we contribute to them with business development and marketing. But the background that applies to this talk is our decade-long involvement with the Square Kilometre Array radio telescope that New Zealand was a full member. And that brought me to South Africa a number of times. So we contributed to the science data processor and the central signal processor in the areas of operating system and the cybersecurity. The reason why I'm mentioning the SKA, because that is the background that will be useful for what I'm going to express later. And we discussed these topics over my conference, Multicore World, over a number of years. And we were fortunate to have Dr. Hpc and Bernard Jans, and even Shiamo Motsegba from Botswana visiting us over a number of years. So we have a long relation with this community. The project that is the topic of today is Listen to the Land, which in Maori, which is an indigenous language of New Zealand, is Whakarongo ki te whenua. Listen to the Land, you can see on that link some brief, but we talk about farming towards 2031. And every time that I mention New Zealand, all the components are generic, are for every mid-sized country. The challenge that every farmer is facing is to do more with less, cheaper, and to stricter standards that constantly change, particularly due to the market, but essentially because the weather is unpredictable, as it has been for centuries, even millennia. So the challenges are not necessarily new. But how we see the farming in a decade? Well, we see it with a number of sensors. And when I say cheap, it's affordable. Technology allows today to have intelligent sensors with computer vision, with artificial intelligence everywhere. And these can be secure, these can be very high-tech specialized sensors, which are monitoring all the biological activity. We can have mini weather stations, we can model local corrections towards the local forecasts, which are still not done at precision, which every little part of the land changes depending of a number of circumstances. So we can monitor the beast, we can monitor the waterways, we can detect the diseases, we can monitor an entire country, not just a farm. But all what I'm presenting in this slide is not new technology. This exists for a number of years, some of them for a decade. But the combination, the complexity of the scale, it's new, it's big. And I'm talking about terabytes per day, several terabytes per day. It's independent of the number, it's a big number, day after day, and you cannot handle that with a series of laptops or iPhones. So the precision farming will generate a massive amount of data year by year that you cannot destroy. You can collect, you need to collect, you need to analyze, you need to maintain, because otherwise, why are you collecting it if you cannot store and create it? And that's the intersection, that's supercomputing territory. And in New Zealand, as in South Africa, we have this expertise. That's where the SKA project learnings from the past decade come handy. The SKA was designed to receive 15 terabytes per data per second. Actually, it was designed for 157 terabytes per second. It has been downgraded due to budget, but we have been thinking in this topic for a decade. And why? Because the sensors that we are using these days, and I'm showing an example from a company called John Deere that presented this one tractor in CES, which is the Consumer Electronics Show, which is the place where you go to present the newest gadgets, the widgets in high-tech electronics. It's not a farming conference. So, and this simple unit is able to process up to 15,000 measurements per second per machine. So you are collecting with a single device a monumental amount of data day after day. And other challenge that I will present in this presentation is the fact that this company is recording 15 million sensor measurements per second across all their machines worldwide. And they are storing in their cloud, they are capturing their data. And the question is, who owns that data? Because your farm, you own the farm, but the data goes somewhere which is not necessarily open. We will talk about this later. Now, how are we going to model all this information? Digital twins is a very generic concept, and some people assume that it's just, okay, let's digitalize. We have an animal Deere, we have land, we have the tractor, let's make a 2D representation. Well, it's not that simple. We're going into models which are much more complex than this, and that's where exascale computing comes handy. The point is that we are going into the concept of systems and systems, and that's the complexity that I mentioned before. You need to consider farming as a system of systems. And I'm not trying to play with words. Everything becomes a collection of a system which forms part of other supply chain of other systems. And the problem when you build a massive system is that it almost always fails. And I'm not being negative, it's the history of mega projects. Now, in order to have a successful large system, let's have small systems. And that's why I'm using this model of agriculture, because if we successfully model a farm, a single farm, independently if it's 1 hectare or 1,000 hectares, is still smaller than an entire catchment or an entire country, then we will be able to have a system of systems which is successful. I put a couple of resources there. One is conceptually very sound but old, and other is recent for people interested in these topics. Now, here we have a slide courtesy of the Wageningen University in the Netherlands about 4 areas coming together. The number 1, decision-making, business and consumers. The number 2, about food integrity. The number 3, about the public at government level, which deals with climate and health and food security. And the number 4 is precisely the technology. And we are converging, we are witnessing the convergence of all these areas. And this could be fantastic or could be a disaster. So it depends on how you build the concept, the topology, and the architecture if you are going to be successful. Now, we are measuring information that comes from sensors. And what are you expecting these sensors to be in the coming decade? First of all, you need to know if this data is reliable and is secure. Because how do you know that the measurements that come in front of your device are true? And let's see that you have a root of trust. Let's see that you manage the risk. Can you share this? I mean, people who have been on the cybersecurity world knows that any system is as secure as the weakest point. Now, when you enter in any industry in particular, do you really know which is your weakest points in terms of data security? It's an open question. I am not trying to answer. I'm asking everyone to think about it, these terms. When I follow telling you that pick your buzzword, and IoT is the industrial Internet of Things, which sarcastically I prefer to call it the Internet of Insecure Things. Why I'm asking that question? Because, I mean, you're combining information from a number of sources through a number of networks, and you really don't know how secure is everything. I mean, I would love you to tell me, yes, everything is quantum cryptographic type of security, but reality tells otherwise, particularly in broad industries like agriculture. And when I say other buzzwords like drones or RISC-V or AI, it's all these topics will be part of that system of systems that we are talking. And if you don't know what is RISC-V, there is a very basic definition. But what I wanted to highlight in the last bullet points are names of companies which are specializing in this new generation of technology. I mean, SI5, it deals with RISC-V, and has been acquired for $2 billion. Sambanova is only a 4-year-old company and already raised $1 billion US. So when I mention my client sample, the early name, the Intels or the Oracles or the NVIDIAs, are not the names that you see here. And that's the challenge that I am posing, that we are talking about mature technology versus new technology. So what is supercomputing? This is just a generic slide. It's Fugaku, the largest and greenest supercomputer in the world. A little photo of yours truly and Professor Satoshi Matsuoka and Dr. Jim Ang. We converge at multi-core world. It's a little bit of propaganda here. But what I'm trying to say is that supercomputing essentially is to solve challenging problems of complexity of calculations at scale. Supercomputing gives you scale and needs open source. All the top 500 supercomputers are based on an open source operating system. The frameworks and AI and machine learning are open source, and the enterprise open source in the new technologies like Edge or AI will be at least at 70% or more open source. So supercomputing needs open source, and you too. Why? Because it gives you these rights. Whatever you're dealing with, obviously code, but technology, hardware, you need to have the right to review what is under the hood. You need to have the right to repair and to keep everything that you have done of that repairs or retain. So when I say beware of black boxes, what are you buying? That's a question that I will ask at the end. If you don't know what you have, do you really own the outcome of what that black box is producing for you? The rate of repair, and I will highlight all the others just with this example. Let's read this together, because the person who signed under these statements, probably you heard about him. But the rate of repair comes through the challenge of corporate consolidation that affect the farmer's ability to repair their own equipment. If you have one of those magnificent harvesters, and for whatever reason they break down because they are in a challenging environment, you cannot tinker with that. You cannot operate because the warranty will be void. That's a challenge. That's a reality problem. And the manufacturers are creating vertical situations in the industry that they try to own everything. Now, we in the IT world have seen this situation 50 years ago on the mainframe era. I mean, the likes of IBM or Digital or others, they used to sell you everything from the box to the software for a single price, which created a challenge on heterogeneity and integration. So who say that this situation is happening? Well, the President of the United States of America, Joe Biden, issued an executive order just a few months ago encouraging the Federal Trade Commission to limit these equipment manufacturers from restricting people's ability to use the independent repair shops. What I'm trying to say is that this is a fact that the transformation is happening. So this has been issued by the White House. I just wanted to highlight this. And I'm converging in this talk into what we submit are the challenges for the decade. The technologies that are being used these days, everything in your cell phone or everywhere, it's outdated. I'm not saying that it's bad, but let's call it mature, but hasn't been discovered last week. Sometimes it's 5, 10 years old. Now, you are trying to bring all this together. It's a heterogeneity challenge, which brings the integration challenge. You can create a company just by being a system integrator for any industry, and you can make a significant amount of money, as it happened in the history of IT in the other kind of systems. And we should add another 2 points. The regulation due to climate change and others, either in New Zealand or in other countries, pose new challenges that you need to face, being a farmer or a systems provider. And when I mention cybersecurity at the end, I'm not talking about ransomware, which is a challenge. I'm talking about concepts like spoofing or tampering the data that comes from that hundreds of thousands of sensors. The adversarial attacks, which that could be a significant cybersecurity risk, a biosecurity risk, not a virus, but you are modifying results that will be compounding with other results. We need to think in terms of challenges for the decade in these 5 points. So I'm inviting all the delegates to the audience to share this vision of New Zealand and South Africa and other countries to reinvent themselves as smart farming center of excellence. We are developing digital farming tools, but it's an ecosystem that we are designing with platforms towards agriculture empowered by supercomputing. And that will be sustained by a topological model. If you think in mathematical terms, we are trying to define the axiomatic, which are the pillars of the building blocks that will create this system of systems. We see it as a nervous digital system towards exascale computing, more than just a simple digital twin. The last 2 bullet points mention some proposals that we are going for funding in New Zealand, but we are open to international collaboration and the New Zealand government as well. 3 slides to finish. The summary. The paradigm change is driven by the huge amount of data and the complexity. You cannot process all the data with your phone and tablet. You need to get used to talk about not just sensors, but also RISC-V, 5G or drones. All these things will be commonplace on a farm in years to come. Think in terms of systems of systems. Think in terms of modeling and simulation, not just static digital twins that model things that happen, but processing in real time towards exascale. You will need, pardon me, have the concept of supercomputing, but not just the monolithic box that I show, but distributed computing at the edge, and you need to get used to open source. Think on terms of these topics for the solve the 5 challenges for the decade. Precision agriculture and smart farming involves a huge amount of data. And we won't process this change in one giant leap. We need to start to take baby steps, but you need to understand the vision from now. We can change our worlds. We can address climate change. We can feed the world in decades to come. So remember, technology around you, particularly in agriculture, it's outdated. Have a look at the market, what's entering in the market, and that's why I try to compare with naming certain companies that maybe you haven't heard of versus the established one. Every edge device at scale will become a data center. You will ignore the 5G or 3G needs. You will process on-site information, and the complexity will be dealt with cybersecurity concerns as well. My final statement. If you don't have control over your hardware or software, if you're surrounded by black boxes, how much of your business you actually own? If you think strategically on those terms, you can stay ahead of your competition. Thank you very much. I'm keen to answer questions.
Thank you, Nicolas, for an interesting presentation. Now it's time for questions and answers. Don't seem to be, there are no questions at the moment.
It's okay.
Yeah, we don't have any questions. But thanks a lot for the very interesting presentation that you gave.
Thank you very much.
Yeah. So we are left with about 7 minutes to the next presentation. So I think what we'll do is that we will wait for that 7 minutes in case there are other delegates that are from other breakaway sessions that they want to join and listen to our next presentation. But thanks a lot, Nicolas, for your presentation.
Thank you very much. My pleasure.
Good morning once again, ladies and gentlemen. We have enjoyed our first talk. Now we are going to enjoy our second talk. Our second presentation will be given by Professor Raesibe Ledwaba. She's an associate professor from the University of Limpopo, and she holds a PhD in physics. Her research interests are in all solid-state battery technologies, utilizing multi-scale modeling approach. She is also involved in human capital development through supervision of students or a postgraduate student. And she also served as a peer reviewer for a journal such as the Surface Science. So she'll be giving a presentation on investigating the pressure effect of structural behavior of Garnet-Type, a solid electrolyte material, a classic molecular dynamic study. Raesibe, the stage is yours.
So the main drive behind the study is the continuous safety issues that occur due to the thermal runaway that is encountered during the operation of lithium-ion batteries. And these have been found to hinder technological development at different scale of battery applications, including electronics and large-scale applications like electric vehicles. This occurs due to what is normally referred to as thermal runaway or thermal instability, which is a result of the heating up of battery materials, particularly the liquid electrolyte, which ignites the battery and ends up breaking down other components of the battery, including the oxide material, which is in the cathode, and ultimately leads it to releasing the oxygen. Now, in a quest to look for alternative ways to remedy this issue, there is ongoing research efforts to substitute this liquid electrolytes with what is called the solid electrolytes, and we are working towards developing what is called all solid state batteries. Now, one would ask, why solid state batteries? These these solid electrolytes mainly have very excellent thermal stability and higher ionic conductivity over a wide range of temperature and yield high energy density during cycling. And that is ultimately what we desire during the charge and discharge process of any battery. Now, in the study, we particularly focus on the Garnet-Type LLZO solid electrolyte materials, and this interest is sparked by its superior ionic conductivity that renders it a more compatible solid electrolyte material as compared to its counterparts. And in addition to that, it is ideal because of its large electrochemical window, its high thermal stability, and its very robust mechanical properties. However, this material has been found to have some setbacks, which are associated with the structural stability and cross-ionic diffusion during cycling, and these affect the overall performance of the battery. And these have been found to be due to the transformation, the structural transformation that occurs when the LLZO transitions from a highly conductive cubic phase to a low conducting tetragonal phase below 630 degrees Celsius. Now, the attempts that have been done to remedy these issues, one of them is ionic doping. Both on the cation side and the anion side have been attempted with several elements, and this ionic doping has been found to largely improve the structural stability while the ionic conductivity remains compromised. So, to our knowledge, there hasn't been much studies on understanding the structure of LLZO under pressure, although we know that pressure plays a crucial role in understanding the structural properties and other properties of materials, and also detecting other possible phases that may occur that cannot be found at ambient temperature. One such study has been when pressure was used during the sintering of tantalum doped LLZO, where it yielded exceptional mechanical properties and also improved lithium ion conductivity at room temperature. So this solidifies our eagerness to explore applying a bit of pressure to the structure and trying to find a material that can still perform optimally without doping. So in this study, we're going to use empirical approaches to study the pressure and temperature effects on this material. Over here, we have the supercell structure of LLZO, which is a 3x3x3 supercell, and it contains 5,184 atoms. So this is the simulation procedure that we followed. First of all, we used the methodized code to generate ground state structures, and further used it to generate our supercell structure with 5,184 atoms. We further went on to utilize the DL poly code to carry out the pressure calculations under the NST ensemble, and after that we took the structures and subjected them to temperature between 300 and 1200 Kelvin under the NPT ensemble. Looking at the equilibrium lattice parameters, we found that at a pressure of 0 and 1 GPa, we still had a tetragonal phase whereby we have A equal to B but not equal to C. And then there was a drastic measure that is observed at 2 GPa whereby we have A equal to B equal to C, and these resembled a cubic phase that occurred. And the following pressures at around 4 GPa up to 6 GPa showed that the C parameter was now starting to deviate from the A and B, and this may imply another phase change in the structure. We then took the crystallographic properties that we found from the pressurized structures. The tetragonal structure was compared with a tetragonal structure from experiments, and we found that they are within 1% agreement, and this showed the efficiency of the structures that we were employing. Secondly, we compared the cubic structure that we found in this work with the cubic structure from literature, and it also fell within a 1% agreement with the experiments. Moving further on, we went to characterize using the X-ray diffraction patterns, whereby we observed that the tetragonal phase structure was containing the doublet peaks that are expected in a tetragonal structure of LLZO, and these agree well with the experimental XRDs. And on the right, we have the cubic phase that was obtained at 2 GPa in blue, and this has singlet peaks that symbolize a cubic phase of the LLZO structure. So this was also sufficient to complement the structural variations that were obtained from pressure. Then here we did temperature calculations. These were mainly done to check the trends that were previously observed in experiments, and these were mainly done on structures that were doped to see if they retain the cubic phase. So we did the same, and we found that the lattice parameters of the 2 GPa structure did not vary a lot when we applied temperature. We actually retained a cubic phase all the way from 300 to 1200 Kelvin. And with the tetragonal structure, we observed that there is a trend that was also observed in experiments whereby the tetragonal phase transitions into a cubic phase beyond 900 Kelvin as seen in experiments. We then moved on to check the XRDs for the heated structures, and in A we saw that indeed at 300 and 600 Kelvin the structure has doublet peaks which symbolize a tetragonal phase, and at 900 and 1200 Kelvins there has been a transition to the cubic phase at the 0 GPa structure. But in the second diagram we observe that there is a consistent crystal structure that has a cubic phase and hasn't varied even at various temperatures. Over here we check the local coordination analysis, which is mainly the bonding between the zirconium oxide and the lanthanum oxide. We found that in both cases the zirconium oxide and the lanthanum oxide have bond length values that were obtained from experiments, and this confirms that the structure that we found can be sustained throughout various temperatures without compromising the diffusion tunnel. The last aspect we looked at was the lithium distribution and diffusion pathways. We checked this at 300 Kelvin and at 1200 Kelvin, where we saw that at 300 Kelvin there are vacancies within the red circles there, and at 1200 Kelvins there is a diffusion mechanism that has been built by the lithiums, and this is what is normally called a vacancy hopping mechanism, and has been seen where the LZO material was doped, and that's where the improvement in ionic conductivity was found. So we can confidently say that the pressurized cubic structure that we generated also has the capability of observing a vacancy hopping mechanism, and that can potentially improve the ionic diffusion. So in summary, we can say that the work was efficiently carried out using molecular dynamic simulations, and it has provided proper insights on the structural behavior of pressurized LLZO, and our results will play a significant role in the structural modification of the LLZO tetragonal phase, and this will set a good foundation of comparing the enhancement routes for LLZO and be able to improve both the structural stability and the ionic conductivity. I'd like to thank the CHPC for this platform to present the work, University of Limpopo and Materials Modeling Center for hosting the project, National Research Foundation, Tutuka Grant for funding this project. Thank you.
Thank you very much, Prof, for the interesting presentation. We know very well that we live in a world where we are trying to move away from a fossil fuel. So this is a very interesting presentation, and thanks a lot for the time and for giving us a presentation. So unfortunately, we don't have questions. This will be all for this session, and we are now going for a break, and please enjoy your break. Thank you all for attending this session and giving support to this session. I thank you. Enjoy your break.